So last class was not recorded, but I also found that some of you found it a bit difficult to follow subgradients. So I will do it. I will do it quickly itself, but I will revise a little bit again and do it quickly. So I will follow the notes, not the slide itself. These notes are uploaded in Moodle. So I will do the subgradient revision again. If you have doubts, then you can ask. So subgradient is defined for functions that are not smooth at a point, and so we say that a vector g g in Rn. So let us say the function is f from Rn to R. We define a vector g in Rn to be subgradient of f if for all z in the domain, if for all z in domain of f, if it satisfies the following inequality, which is fz is greater than equal to fx plus g. Okay, I can use this, or let me use this. So g z minus x, where this is defined to be g transpose z minus x, right? So any g, vector g, that satisfies this inequality for all x and z, we will declare that to be a subgradient. So if it so happens that f is convex and differentiable, then the subgradient is the gradient itself, right? So then subgradient is the gradient the usual gradient of f. So as I have said before, this quantity here, fx plus g z minus x, is a global underestimator of the function at x. Okay, so I draw this. So this is the line fx plus g z minus x. So this acts as a lower, okay, acts as global for the moment we keep f convex. So acts as a global underestimator. And we have also, if we collect all those possible gradients, then we can form a set subdifferential. Okay, so that's fine. And so the subdifferential is the collection of all g such that fz is greater than equal to fx plus g transpose z minus x for all z and x in domain of f. Okay, so formally I define this subdifferential set. It so happens that the subdifferential set is a convex set. Okay, why it should be, right? The subdifferential of f at a given point x is a convex set in itself. So del fx is a closed and convex set, is closed and is closed and convex set. This is because it is seen as it can be seen as an intersection of convex sets. Okay, and we know that intersection of convex sets are convex, and they happen to be closed also. If some of you don't know about the closed set definition, you can skip that for the moment. It's not very crucial right now. So at least you know what is a convex set. So intersection of so can we write this as an intersection of convex sets? Okay. It so happens that we see this set of G's here, and then this defines a plane here. So we can write this as an intersection of convex sets, in fact half spaces. Okay, so half spaces in the sense that, so half space, recall half space. So half spaces are set of all x such that A transpose x is less than equal to B. Okay, so this is how we define half spaces, and essentially half spaces. So if we can say that x is in Rn. Okay, then so obviously A and B are A is in Rn, B is a number. So half spaces, by the name, they divide the space into two parts, right? So this can be a half space in R2. So on this half you have one part of the space, on this half you have another part of the space, depending on where the A is aligned. If A is aligned in A is this direction, then you have all the entries, all the x that satisfies A transpose x greater less than equal to B on one side, and if your A is this way, then you have the other half space, and so on. Okay, so half spaces necessarily divide your space into two parts, and this is also in higher dimensions. So if I'm in the ambient space is Rn, okay, then this is a hyperplane, okay, and n-1 dimensional, and I need that hyperplane to partition the space into two halves, right? Okay, so if I look into this, then for a fixed Z, right? So for a fixed Z, if I vary G, then it's like G is acting like an X here, okay, and then Z and X I fix in some way. Okay, so let us say Z, so Z minus X transpose. Okay, so let us say I fix for a given Z and X, and I'm looking for all possible G. Okay, so this is less than equal to Fz minus, which is also known because I fixed Z and X. So this seems to be the characterization in terms of the half space. So these guys are known, so I take this as a B, and this guy I take this as an A, and this I take this as G as an X. Okay, so then I can intersect these half spaces, and this will essentially characterize the subdifferential. Okay, so it's a roundabout way of writing this set as an intersection of half spaces. So let me write that down now. So this is a fact, and the proof of this fact comes from the fact that we will write this as an intersection, right? So del f x is intersection over Z in domain of f, and this is over all G such that Fz greater than equal to fx plus g transpose z minus x. Okay. So if you want, you can go ahead and prove this. I have given you some intuition, but if you want, you can go ahead and prove that this is indeed equal to this. Okay. So you can use this set is a subset of this, and this set is a subset of this. Okay. So then you prove the equality. So what we know now is we are so this is the half space. Okay, and we are doing an intersection of the half space for all z. It could be arbitrary intersection, but arbitrary intersection of closed set is closed, and arbitrary intersection of convex set is also convex. So these being convex and closed, okay, as I said, you may not know about closed set, but you can ignore that. Okay, so this being closed and convex, the arbitrary intersection of this is arbitrary because z could be infinitely many, right? So the intersection is over arbitrary intersection of closed convex sets is closed and convex. Okay. So we use the fact that arbitrary intersection of closed set is closed and convex also is convex, and so this tells us that the subdifferential set is a convex set. Okay, it's necessarily a convex set. Okay. Moreover, if f is continuous at x, if f happens to be continuous at x, subdifferential set is also necessarily bounded. Okay, bounded as a set. Okay, and intuition behind this could be that if f is not continuous, right? If f is not continuous, then what can happen, right? So not continuous means either there is a jump. Okay, so let us say there is, I mean, at this point there is no value defined, so this is a not continuous function. Not continuous function, right? Now if I am going to define, if I am going to take a subdifferential, right, at this point, then the set is subdifferential set is going to be necessarily bounded, because I am going to consider all possible tangents that I can draw, right? But then the fact that it stopped here arbitrarily, this one is also allowed, right, which is infinity, right? So you kind of get all these values, right? So it is unbounded. Okay, the subdifferential at that point will be unbounded, because although it takes valid values, but then the fact that it's there, the tangent can go and become infinity also. Okay, so then it becomes unbounded. So the only way, so far so good, a closed and convex set is there, but still can remain unbounded. So the one way to prevent it from being unbounded is when f is continuous. Okay. So so from this intuition we can also say that if f is continuous, then del f is bounded as a set. Okay, we can concretely prove this, but it's not required. So subdifferential of a differentiable function is the trivial one, which is just the so subdifferential if f is differentiable, then subdifferential just contains the usual. Okay, so this is just a repeat of what we have seen already. So it can also be said in a converse way. If it so happens that subdifferential conversely, if it so happens that subdifferential is a single vector, then necessarily f is differentiable. Okay. Okay. So if it is a singleton, then this implies f is differentiable. Now I will define something called directional derivative. So if you are in a real line, then there is a concept of derivative along an axis, right? So that's the only derivative you have, right? But as soon as you move to higher dimensions, you may take derivative of a function in variety of ways, right? So in any direction you want, right? So we can define something called directional derivative. So if you recall the usual derivative, then let us say f from R to R, then this is limit h tends to 0 fx plus h minus fx by h. So on real line you only have one possibility. Okay, you go like this. But the moment I change my functions from f from R2 to R, okay, so here let us say the function is defined like this, then I'm computing if I go in this direction, how the function changes, right? But then if I go from R2 to R, I have multiple possibilities, right, to go from. So if it's my domain is like this and function is like this, it takes values for these. So now if I am here at point x, okay, let us say some coordinate x1, x2, then I have multiple ways to ask how the function varies. If I go in this direction, then I would like to know how the function varies here, right? So maybe it is along this curve, okay, and then maybe the function is varying more around this much, okay, along this. But then I can also ask, what about this direction, what about this direction, what about this direction? So essentially you have infinitely many possibilities now to compute, look for the changes in the function values in multiple possible directions, right? So if this point is a vector x, then I can ask for TV, where v is some direction, this one, it could be this one, it could be this one, okay? So then instead of making an increment in x by h, I may want to generalize this to TV now, okay? And let the t go to 0. So this will act like instantaneous change I want, then t will be tending to 0, okay? So overall TV will be tending to 0, okay? So then there is a concept of directional derivative. So I want to know the change in the function along certain direction, right? So let us define a directional derivative, which is simple, just change h by TV. So let us keep things for the convex right now, okay? So for convex functions f, the directional derivative of f at the point x in Rn in the direction of v, at the point x in the direction of v, in the direction of v, is given by f prime x. And now we also include a v, because there is a parameter v now along which I may want to check the gradient. So this is defined to be limit t tends to 0 and f of x plus tv minus fx by t. Okay, so we have generalized the definition of a derivative for higher dimensional problem. There is a result that I may not prove, but it relates to subgradient. Okay, I will write that and without proving it. Okay, so the directional derivative, all the derivation is there in the notes, but I will skip it. Okay, so the result we have, so let us write this as a fact, is f prime xv is supremum over g in subdifferential of f x g transpose v. Okay, so this relates directional derivative with the subdifferential. So directional derivative at a point v, at a point x along the direction v is supremum of all possible g that you can find at the point x, and you apply on v and see which one gives you the maximum value. So directional derivative happens to be the one that gives you the maximum. Okay, it kind of picks it picks g for which g transpose v becomes the maximum. Okay, so we can prove this. In fact, this is there in the notes, but let us skip this. Okay, so we will keep this in mind. Okay, then we have done calculus of subgradients, right? So let us have a look at that calculus of subgradients. So just like the usual derivative, classical derivative, we also want to know what is the subdifferential of a sum of a function, right? What is the subdifferential of a scalar multiple of a function, and so on. So we try to put this in one place. So for alpha greater than or equal to 0 scalar, if I take a subdifferential of alpha f, then alpha comes out. So there is no surprise here. It's similar to the usual derivative. And sum and integral. Okay, sum and integral. So if f happens to be f1 plus f2 plus dot 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 plus fn, fm let us say, and f1 fm are convex, so it's important to note that for the sum, okay, subdifferential of f will be sum of the subdifferential. It happens only for convex function. If it's not convex, it's tricky. Okay, so if these are convex functions, then we can write in this case subdifferential of f is sum of the subdifferential of okay, obviously all at x, right? This is true only if f are convex. Okay, and then we have affine transformations of domain. So in this case, if we have an h which is f of ax plus b, then the subdifferential of f or h is A transpose subdifferential of f at ax plus b. So this is also not a surprise. If I would have taken a gradient also, I would have got same thing here. I would have got a gradient here. Then we have pointwise maximum. Pointwise maximum. So suppose f is a pointwise max of f1 to fm. That is, fx is max of I1 to m fix. So it's usually non-differentiable. Any max mean functions are usually non-differentiable, especially at the point where fi's cross each other. So what would be the subdifferential of f, okay, at those points? So let k be any index for which fkx is fx, and let g be in the subdifferential of fkx. If g is in the subdifferential of fkx, then since fkx is fx, g is also in the subdifferential of f. So this implies g is in the subdifferential of f. So the plan here is to find one of the subgradient of fx at x. We can pick one of the subgradients of the function which happens to be the maximum at that, okay, because fx will pick the maximum, okay. So we can pick the one, let's say the k for which fkx is fx, and we can pick the subgradient of fk, okay. So to find the, so let us first write down words. To find a subgradient of maximum of functions, we can choose one of the functions, that achieves the maximum. At that point. And choose any subgradient at that point, okay, of that function, and choose any subgradient of that function at the point. So if we do that, if this is our plan, then can we verify that, right? So if this is the case, then can we say that by doing this, one of the subgradient of the function that is the maximum at that point, if we do that, will it be a valid subgradient of fx itself? So we can try to prove this. Okay, so fz is fz, let us say I take any point z, okay, then fz will be greater than or equal to fk at z, because f happens to be the maximum. So indeed fz is going to be greater than equal to fk z, because f happens to be the maximum of all the fi's, okay. So that's clear. And fk itself will be greater than equal to, since I am picking the subgradient of fk, okay, which is the g, let's say. So according to that, fk of z is greater than equal to fx plus g subdifferential of fk, okay, g transpose x minus z, okay. So the fact that g is a subdifferential of fk, that's what I'm trying to just write this here, right? So fkz is greater than equal to fkx plus g transpose z minus x. right? Because this is because G is in the subdifferential of Fk. That's the definition of being a subdifferential. And what are we trying to prove? We are trying to prove that G is also a subdifferential of Fz. Okay? So essentially we have to prove an inequality that Fz is greater than or equal to Fx plus G transpose Z minus X. Okay? So what can we write from here? Fkx is Fx. Okay, that's picked by Fx. So Fkx is Fx, and there seems to be a typo here, I believe. I should not change Z to anything else. So Fkx is Fx plus G transpose Z minus X. Okay. So this necessarily tells me that G is this implies G must be in the subdifferential of F at X. Okay. So we have proved that if we are going to find a subdifferential of F, which is a max function, then let us say that at X, F finds the Fi which gives the max is the K1, right? So then in that case Fx is Fkx, and you now just have to find one of the subdifferential of Fk at X, and if you do that, that happens to be the subdifferential of F itself. Okay, so this is what we have tried to prove. And in the last class we also have written the convex hull thing, right? And so essentially if I want to find all possible subgradient of F, in this case I found one, but if I have to find out all possible, then I have to take a convex hull. Okay, so if I have to write the subdifferential set, which is a collection of all the subgradients, so this is a convex hull of the union of subdifferential of Fix such that Fix is Fx. Okay, so you are supposed to take a union of the subdifferential of Fix wherever Fix is Fx. Okay, in only those cases, because F is the supremum of these Fi, right? And then take a convex hull. Okay, so if we want to look into this in the form of pictures, then let us try to create something. Maybe let us stick to 2, right? So we have F1 and F2, and we are supposed to find the pointwise max. So this is our F1 and this is our F2. So if we pick the pointwise max, then we pick this guy until here, and then we pick this guy from here onwards. It will be good, maybe because we have a convex hull, it will be good to also create one more. So then in that case, and then it starts picking from here. So this is my another one, this is my another one source of this non-differentiability, and F is the pointwise max, which is the dotted line, right? So this is our F, right? And we are supposed to find the subdifferential at any given point. Okay, so let us see some arbitrary point where there is no non-smoothness. So let us say this point, right? This point F is F1, right? So at this point F is F1, right? In fact, f is f1 for all these x, right? So in this case, from the previous one, k is 1, right? So at all these points, right? At all these points until here, because after here some other I is picked, right? Fi. So, but for all these points until here, we have these gradients, these gradients, these gradients. These are the usual gradients. So obviously subgradient also involves the usual gradient. So for all these x, I will have all these angles, right? So covered, right, until here, right? So basically this angle until this angle, right? This angle and then this angle. So let us say those angles are like theta 1 up to theta 1 up to theta 2, right? So theta 1, theta 2. So that's the range theta 1 to theta 2 until here. F is picking f1 all the time, and the subdifferential, because it's smooth here, so the differential is just one number unique derivative until here. So I have collected all those here, and then here it's more interesting, right? Here it changes, right? So here fx is both f1 and f2 also, right? So because this guy is also equal, right? So here fx is f1x and also f2x. So you are supposed to take all those subdifferential for f1 and subdifferential for f2, right? So let us put this as x1 and this as x2. So if I write down the sets and the things that I have in the set, first thing I have theta 1, theta 2. That was until here. Here I have subdifferential of f1 and subdifferential of f2. So I append this by subdifferential of f at x1, subdifferential of f at x2. Okay, and then it carries over to, so let us say this was for f1, and then from here to here it will be some other picked from f2. Okay, and then at this point again, now at this point I have f2 and f3, right? So then we will append del f, it is at x2, and del f, so this was del f2 and del f3 at x2. Okay, and you are supposed to take a convex hull of this. Okay, so rather than taking a union, I have just taken this, and so basically I just have to do now convex hull of this, right? So this is what it means. But there is problem with the notation right now, is it is defined for single x. Okay, so I have to be a little bit careful here. Rather than appending all this says that only at x. What I have done is that I have accumulated for all x. So this is not necessarily correct. So what I'm trying to say is that this will only become interesting when, because convex hull at this point I have just one point, one derivative, right? So this, which is picked by del f1 at x. Okay, so this is my x. So the convex hull of one number is the same number. So nothing really happens here. So these are usually defined like this, but here is something interesting happens, right? Here you are supposed to take x1. At x1 is something you are supposed to take a convex hull. Okay, so let us do this specifically, right? So let us say my x is x1. Then this is convex hull of del f, and this is picked by f1 at x1, and del f, another one is f2 at x1. This is the convex hull I have to take to report the subdifferential of f at x1. Okay, and this essentially means that you basically take all this. Okay, and similarly you do it for x2. Okay, so we have to do it for point-wise point, right? So between x1 and x2, these will be singleton. So convex hull of singleton number is same number, but here again at x2 something interesting will happen, because you will have del f2 and del f3, right? And then again it will be singleton. Okay, so this max function could be generalized to an arbitrary index set. So a very easy generalization of this is when my indexing goes to some arbitrary index set A, and max is replaced by supremum. So supremum fx is supremum of now alpha coming from some A. So alpha is the indexing here. So in this case I will straight away write this. It's a similar thing here. So this will be convex hull of union of del f alpha x such that f alpha x is fx. Okay, so this is a simple extension of that. So we can skip that for the moment. Okay, so I think with this it should be okay with the subdifferential. That's all we have for the subdifferential. Now we move to something called duality. So I'm going to rub this now. We'll start from here now. So I'll do a quick duality concepts, Lagrangian dual function, KKT. Okay, we will need this again and again. Okay, so given an optimization problem, so let us look at an optimization problem which is of a generic form given by minimize f naught x subject to, so inequality constraints are there. So f I x is less than equal to 0 for I equals to 1 to m, and h I x equals to 0 for I equals 1 to p. A generic optimization problem will have some objective to be minimized and then some inequality constraint and equality constraint. So here x is in Rn, and we will assume that the domain which will be the intersection of all these, okay, so which is the intersection of a domain of Fi, intersection of domain of Hi, okay, is non-empty. So I equals 0 to m, I equals 0 to p is non-empty. And we do not assume that the functions are convex. Then there is something called Lagrangian. So I will define a Lagrangian. So this is a function L from Rn, then Rm and Rp to a real number R, and it is defined as follows: L x lambda nu is f naught x plus sum of lambda I fi x and I equals 1 to m plus sum of mu I hi x. Equality constraints go from 1 to p. Okay, so we define, for a given optimization problem, we define a Lagrangian like this. So obviously the domain of the Lagrangian is D cross Rm cross Rp. Here lambda i's and mu i's are called Lagrange multipliers. So here lambda i's and nu i's are called Lagrange multipliers. Sometimes lambda I and nu I are also called lambda I, nu i's are also called dual variables. Okay. So this is one of the first ingredient, and then the next ingredient is Lagrange dual function. So Lagrange dual function, and this is defined as g lambda nu, and we do the infimum of the Lagrangian, okay, for x. So since we infimize the Lagrangian for x, only lambda and nu will be remaining, okay. So we do L x lambda nu, which is infimum of x in D, and we have f naught x plus lambda I f I x plus nu I h I x. Okay. So we define a new function which is Lagrange dual, which is infimum of the Lagrangian. It so happens that the Lagrange dual function is a convex function in lambda and nu. So note that g lambda nu is convex in lambda nu, and this is true because this is not convex. Actually, it will be concave because it's infimum. Let's say the other way around, right? Supremum is convex, infimum is concave. So g lambda nu is concave in lambda and nu. So there is another result that infimum of concave functions is concave, right? So recall infimum of concave is concave. Just like supremum of convex function is convex. So concave is like negative of the if the negative of a function is convex, then it's called concave. Okay. Basically you flip it. Okay. So it's true because it's an infimum of, these are linear in nu, lambda and nu. Okay. You can forget this. These are already like covered here. So these are kind of because as a function of lambda, x is seen as a constant. So these guys are like a constant for us. So the only thing there is lambda and nu, but lambda and nu are linear there. Okay, there is no square or anything there on lambda and nu. So this is a linear function in lambda and nu, and linear functions are concave. In fact, linear functions are both concave and convex. Okay, so we can say it's an affine. Okay, to be more precise. So affine, because linear necessarily has to go through origin, but sometimes we misuse the definition. Okay, so this may not be kind of 0. Okay, so for linear this is linear, but with this it's affine. So this is a linear function. Linear function is both concave and concave because it's flat, right? So it's both way you can think of, right? So it's an infimum of concave functions, right? And if infimum of concave function, we know a result, okay, because I can change the supremum definition to derive this. So supremum of Fix, okay. So I change minus and then put a minus here. Minus of that makes it infimum, and then so the result on convex is easily transferred to infimum of concave in concave. So that's it. So that proves that G lambda nu is concave because it's the infimum of concave functions in lambda and nu. Okay. So this is a good result, and we will see why. So sometimes solving a problem in a dual forms, I did not say how I will solve this in a different form, dual form, but I will come to that. So let us look into lower bounds of the dual function. Let us understand this function a little bit. So lower bounds. So the claim is that G lambda nu must be less than or equal to P star, where P star is the optimal value. P star is the optimal value of the original optimization problem. Let us say this is star. This means that this is the minimum value of f naught x. We want to minimize. So if we find the minimum value, we denote it by P star. Okay, so that's what we are saying here, where P star is the optimal value of let us say it's a primal problem. So let us use a P here. Okay, so that we recall this again and again. So optimal value of P. Okay. So how do you prove this, right? Why should it be the case, right? G lambda nu must be less than or equal to P star. Okay. So let us try to prove this. Okay. So suppose x bar is a feasible point. Now feasible point is a point that satisfies all these, right? So first define a feasible point. So a point x is called feasible if it's first of all in the domain of all this, and then it satisfies the inequality constraint and equality constraint. Then we say that at least there is a point so that I can work on the optimization problem. So let us consider x bar. Now continue from there. Let x bar be a feasible point, okay, for the optimization problem P. Then for P, so in that case it necessarily satisfies the inequality constraint. So fi x bar must be less than or equal to 0. Then fi x bar must be less than or equal to 0, and hi x bar must be equal to 0. Okay, and in the Lagrangian, one thing to note is that these lambda i's are greater than or equal to 0. Okay, so the reason why lambda is greater than or equal to 0, because we don't want to flip these guys, right? These are inequality constraints. So lambda i's are greater than or equal to 0. So this is what we have for the feasible point. So I guess this hi's will vanish, right? So and then fxy's will be replaced by inequality and so on. So let us see the consequence of this. So then we have so if we'll just look into the last two terms of the Lagrangian, then we have lambda I fix I equal 1 to m plus sum of mu I hix I equal 1 to p is less than equal to 0. Okay, and I mean this is for x bar. Okay, so this guy is 0, although we have written this because hix is 0 anyway, right? So we just keep it as a dummy, and this guy is already less than equal to 0, lambda is greater than equal to 0, so overall everything is less than equal to 0. So now we look into the Lagrangian. So if we look into the Lagrangian, then so if we write down L over some x tilde, let us say, okay, this is not the x bar, or it is the x bar actually. Yeah, let us continue to look at the x bar, lambda nu. Then this is f naught x bar plus everywhere it's x bar, lambda I fi x bar plus nu I hi x bar. Okay, so what does this give me? This gives me, because this guy two terms are less than equal to 0, so overall the whole thing is less than equal to f naught x bar. Okay, so from there now we can go back to g lambda nu, and we know that the Lagrangian is less than equal to f naught x bar. So obviously g lambda nu, okay, will be also less than equal to infimum of f naught x bar. Infimum of all f naught x bar for all feasible will be p star. So from there we get g lambda nu is less than equal to p star. Okay, because p star is the optimal, right? So the minimum of this. So f naught x in general is less than equal to f naught x in general is greater than equal to p star, because p star is the minimum possible, right? And x bar is any feasible point. It's not necessarily the point at which it becomes a minimum. Okay, so x bar is any feasible point. You can also write like this: f naught x bar is, so p star is less than equal to f naught x bar. Okay, so so this is what we have, and then g lambda nu, let us look into this. G lambda nu is infimum of Lx lambda nu. So this overall is less than equal to f naught x bar. So g lambda nu, which is infimum over x in d L x lambda nu, and this is less than equal to L x bar lambda nu, because this is the infimum over x. So if I take any arbitrary x bar feasible, it must be greater or equal. Okay, and we know that this guy is less than equal to f naught x bar. So what we have proved is that g lambda nu is less than equal to f naught x bar for all x bar feasible. So this is true for all x bar feasible, so obviously it should be true for the smallest possible also. Okay, so this implies that g lambda nu it must be less than equal to p star. Okay, p star is the minimum of f naught, minimum of all possible f naught x bar. So from there we know that the dual function is a lower bound of the primal. Okay, p stands for primal. This problem is called primal. Okay, and reason why we say is primal, because there is also a dual variant of this. Okay, and this dual variant actually comes from this. So what we do is that we actually, if we maximize this, okay, because this is giving me lower bound, right? So it seems like one way to approach p star is by maximizing this, because P star is somewhere here, and this is what I want. And G lambda nu is some quantity which is less than equal to this, and it's always less than equal to P star for lambda nu. Then another approach to solve this problem is I maximize G with lambda nu. Then can I get exactly equal to P star? But that's not always the case. There is something called duality gap. So maximizing this function with lambda nu is a dual problem. Okay, you are trying to solve your primary problem via some. So usually what you will do is that your problem is like this. You minimize your problem. So then you are coming from higher value to lower value, because that's a minimization problem. And the dual tells you that construct G lambda nu and start maximizing. So you approach your problem in a different direction. Okay. So that's the idea behind the duality. You solve your problem via dual function. Okay. And as I said, you may not exactly reach at P star. Okay. But even if you reach close enough, it's fine. Okay. So if we solve some problem, usually, so in one of the paper on completion problem, so this is our duality gap. So then we prove that, okay, we go via dual, but then our duality gap is going to 0. Okay, it's a tensor completion problem applied to images, image completion, and so on, even recommender system. So these are the type of things you may have to do. Okay, you go via dual, but then even if you don't prove that it's going to 0, maybe characterize the error that you are getting by proving a duality gap. Right? Okay. So we can look into one example, practical example of solving via dual problem. Okay. So you can look at more examples from the book. So let us consider least square solutions. Okay. So consider minimize x transpose x subject to Ax equals to B. So this is our f naught x. This is our inequality constraint written in matrix form. But if we split this, then it will be like if A is like P by n, okay, then we will have P equality constraints. Okay, each row of A will give me one equality constraint. Okay, so if we want to solve it via dual, then we have to first construct a Lagrangian. We have to infimize the Lagrangian over x. Then the resulting G lambda nu that we get is a dual function, and we will maximize that over lambda nu. Okay, so that's the plan. So in this case, the Lagrangian will be x and nu only, because there are only equality constraints. So only nu is there, lambda you don't have to consider, okay, because there are no inequality constraint. So L lambda x nu will be basically this plus lambda times this. So x transpose x plus, since this is written in a vector form, the nu I will choose will also be a vector. So nu transpose Ax minus B. So nu obviously will be P length, okay, because this is A is like this, P by n. So nu should be of length P. Okay, so this is nu, this is A. Okay, so this is our Lagrangian, and we are supposed to infimize this. We want to get rid of x. Okay, so we are supposed to infimize and then get a just G nu. Okay, because lambda is already not there. Okay, so in this case the Lagrangian we have, and this Lagrangian, the domain of the Lagrangian is x comes from Rn, okay, x from Rn, and nu is from P. So it's like Rn cross Rp. Okay. Now we are supposed to infimize the Lagrangian. Okay, so the dual function G nu is given as infimum over x of L x nu. And now we are supposed to solve a optimization problem. Okay, our original goal was to solve a optimization problem, but while going to the dual we have to solve intermediate optimization problem to get the dual function itself. Okay, so this is infimum over x and x transpose x plus nu transpose Ax minus b. Now the question is, can we solve this, right? And we are supposed to do this, solve this for x, right? Now we have to look into this, right? What type of function is this, right? This seems to be a quadratic function, right? Quadratic in x, and if we invoke the, if you recall the result that we had, that to check the convexity, right? So we had convexity definitions which was like line definitions, right? So theta fx plus 1 minus theta fy is greater than or equal to f of theta x plus 1 minus theta y. Okay, that's the line definition, line always above the curve. Okay, then we had the first order condition, right? So fy is greater than or equal to fx plus grad fx y minus x. That's when the function is at least one times differentiable. Then you can use this first order condition for convexity. And then the third one was simply grad square f being positive definite. Okay, so we have done all this to check in any one of these way a function is convex or not. So in this case it's a minimization problem, and if it so happens that this is convex, it will be easy to solve for, because a convex function necessarily will have minima where the gradient becomes flat, right? So the moment I know that it's a convex function, minima will be easy, because I will just take a gradient of f, in this case is this, and equate it to 0, and the x that I will get will minimize this. So can we check any of these, right? So this sometimes can be easy, but we have to check whether it's 2 times differentiable. Okay, it looks like 2 times differentiable. Okay, they are like square terms and so on, so it's very easy. So this guy is twice differentiable, I mean more than twice also, but at least twice differentiable. And if we check that gradient of this guy, so grad square of this, and grad square happens to be what in this case? What is 2 times derivative of this? What is this? If I take 2 times derivative, what do I get? What did you say? Identity, right? Identity. Okay, so this we get is identity, and identity is always positive definite, right? Because all the eigenvalues are greater than or equal to 0. Okay, you can also check by x transpose Ax should be positive, right? Okay, so this is convex. Okay, so this implies it is convex function, right? Now it is a convex function, so now I am pretty sure that I will just take a derivative and equate to 0 to find the x for which this will be minimized. Okay, if it was not convex, then this is not good enough, because it can be flat at many places, this way, this place, this place, this place. So you don't know which one, right? And even if you know, and there are many possibilities for becoming flat, you cannot check it by hand, right? But if it's convex, then it's very simple. There is only one minima, and which is the global minima. Okay, so then we can easily minimize this, right? So we have so let us say this is grad x of this, right? So we will do one derivative, right? So grad x of x transpose x plus nu transpose ax minus b. Okay. So if we do a derivative of this, okay, what do I get? 2x plus a transpose v. 2x plus a transpose v. Or v or like nu. Okay. And then we equate it to 0. And I believe it will be a least square solution because a is not square, right? A is p by n, p may be less than n. So you may not be able to invert it, but you may be able to solve this. Oh, I don't need to invert this, sorry, because yeah, I was wondering. So because I have to solve x for x, right? So this should be equated to 0, and solving for x is easy, right? So x is half, and there is a minus a transpose nu. Okay. So this is the x that is supposed to minimize this. Okay. And we put in the value of x, and then we get expressions only in nu. Okay. And then you are supposed to maximize, right? So g nu will be, in this case, let us say g nu somewhere here, and then you will try to maximize this to reach to the primal. Of course, you may ask, like, even if you maximize this for some nu, but what is the x after that, right? Because I maximize in terms of nu, right? But how are nu and x related? Because someone who gave you this optimization problem, they want x, not nu. Okay. So you have found the value of the f naught for certain nu star, but how are nu star and x star related? X star is the primal optimal that I want, which x star is the one that minimizes this, right? So yeah, we will see that how, but let us for the moment try to maximize g nu also. So at least the first step is, what is g nu? We know now. We have infimized this, so g nu we can write. Okay, so we can write a g nu. So we have dual function is g nu, which is Lagrangian of, so we will substitute minus half of a transpose nu, and that comes out to be minus 1 over 4. You can check this, okay? Minus 1 over 4 nu transpose a transpose nu minus b transpose nu. Okay, you substitute that here, and that's what we get. Now we are supposed to maximize this, right? So now we want to maximize this. We want to go to p star, right? So now we have to do the supremum of this, of g nu in terms of nu. Okay. So what is the supremum of this, right? Supremum of minus 1 over 4 nu transpose a transpose nu minus b transpose nu. Okay. If it happens to be convex or concave are the same thing, right? So if it happens to be concave or convex, I have easy way to solve this again, just like I did it here. Now we have to ask whether it's concave in mu or convex in nu, right? If it's so, then we can solve this again by taking the derivative and equating to 0 and so on. Okay, so this is a supremum. So if it happens to be concave, it's very nice. Okay, because if it happens to be concave, then supremum, which is the maximum value, it will again be characterized by grad g nu being equal to 0. So it will be characterized by, again, the gradient becoming flat. Okay, so then we have to check whether it is a concave in nu, right? So how do we check whether it's concave in nu?
I would tell you that more or less everything gets reversed, I guess. This inequality gets reversed. This also, I believe, gets reversed. This certainly gets reversed, and this also gets reversed. So now it should be negative definite if it has to be concave. So let us check if the double derivative of g is negative definite, right? So let us do this. Grad square with nu of g nu. So is this, what is this first of all, right? So what is the double derivative of g nu? A transpose and something is missing, right? That's the crucial one. Just A transpose or more? Negative is there, right? Negative we should not forget, right? And half will also be there, I think. Only 1, 2 will go away because of new square terms. The 1, 2 will go away. So this will be minus half of A transpose. Okay, so now we want to know what about A transpose, right? So is A transpose positive definite, negative definite? What can we say, right? But because nothing is given for A, right? A is just P by N. So A transpose, if I do, then I get a matrix which is P by P, right? So what can you say about A transpose? Is positive definite, negative definite? What can you say? For any matrix A, I'm asking, what can you say about A transpose? Is it necessarily positive definite, negative definite? Yeah, it is symmetric for sure, but what about positive definite, negative definite? It is positive definite, right? Necessarily for any A. And why is that? I will check the definition itself, right? The positive definiteness tells me that X transpose A transpose X, is this greater than or equal to 0? That's what we are asking, right? But this is, right? This is norm of X, right? So we have to check, yeah, X transpose. Yeah, so basically it's A transpose X. So A transpose X. Okay, this I can write like this, and then transpose, and then A transpose X. This is basically norm of A transpose X. So norm is certainly greater than or equal to 0, right? So for any matrix A, we know that A transpose is necessarily positive definite, but the fact that there is a negative, it makes it necessarily negative definite. Okay, so then since this is negative definite, by our criteria that if it is negative definite, then the function is necessarily concave. Okay, so this implies G is concave. Then since G is concave of this form, then I will just take the gradient of G with nu and equate it to 0. Okay, so if I do that, then so in this case the gradient will be A transpose nu, okay, minus B, okay, and yeah, I think 1/2 will be there. Yeah, and yeah, so and then we will solve for nu. Okay, so we equate it to 0 and solve for nu. Okay, so if we do that, so since this is concave, we do grad nu of G nu and equate it to 0. Okay, so this implies minus 1 by 2, right? Minus 1 by 2 A transpose nu minus B. I mean, yeah, minus B, and this should be equated to 0. Okay, in this case, it should be A transpose A, right? It gets transposed. A transpose A nu minus b equals to 0. So in this case, to solve for nu, we need to take the inverse, okay? And if it's rank deficient, that will create another problem, but for the moment we can think of some pseudo inverse. So nu will be minus of A transpose A inverse of B, okay? So this is the mu star that we are looking for, okay? This is exactly when A transpose A will be like n by n, okay? So if it's like a full rank with n, then it's invertible, and this we substitute in G, okay, and that will give us the dual optimal, which will be D star, okay? Okay, so what we have done is that with this we have, this is our x star, and this is our nu star, okay? So this is our G nu star, and this is our F naught x star. So there may be a gap, okay? The duality gap also we may have to, I mean, kind of we can check. So this is P star, this is D star, okay? Or maybe we have solved this problem exactly, okay? This will be quantified if the duality gap is 0, but for the moment this is the best we could do via dual, okay? This is the best we can do, okay? Now the only thing is how big is this, right? Is the duality gap. Okay, so this problem tells you that to solve a constraint optimization problem, this is interesting for constraint optimization problem because your Lagrange variables come only via constraints, right? So if there are constraints, then it makes sense to solve via dual, okay? So when there are constraint problem, you can solve a given problem via dual, okay? So you first form the Lagrangian, okay, and then you infimize the Lagrangian, you get the dual function, and then you maximize the dual function. That's another way to solve a constraint optimization problem. I will come to the fact that how I get x star from nu star, okay? That's let us keep it, but we can derive x star from nu star. So this is so we have seen conjugate functions, and conjugate function can be used. It's useful. I told you that it will be useful when we do the duality. So let us see how conjugate functions can be used. So recall that, okay? So Lagrange dual function is the G function, right? And Lagrangian is just the L, okay? So you should not get confused. Lagrange dual function is the G, and only Lagrange function is L, okay? And conjugate, right? So let us see how conjugates can help us in getting the dual. So recall what was conjugate, right? So conjugate was defined as f star y, which is supremum of x in domain of f, and then y transpose x minus fx. This is how we defined a conjugate, and regardless of f being convex or not, conjugates are necessarily convex, okay? Because it's a function of y, and in y it's linear. Supremum of linear functions is it's linear, hence convex. So supremum of convex functions is convex. So all this we recall. Now the question is how it is useful, right? How it could be used in using solving a problem via dual. So let us see that. So conjugate and Lagrange dual function are related. Conjugate and Lagrange dual function are related. So let us see in this way, minimize fx subject to x equals to 0. So let us see this simple optimization problem, constraint optimization problem, and let us form a Lagrangian of this. So Lagrangian of this is L x nu, and this is fx plus nu transpose x. So I've just formed a Lagrangian of this. Okay, and let us look into the Lagrange dual function, which is g nu. So g nu is yeah. So we will do the infimum of L infimize over x, and then we get the g nu, right? So this is fx plus nu transpose x. Okay, so we want to do the infimum, and this we want to relate it to this, right? So to relate it to this, maybe we want to change infimum to supremum somehow, like we will kind of rearrange things, right? Nu transpose x seems to be identified with y transpose x, so there seems to be some relation with y and nu. So this is somewhat looking like y, okay, right? So this is nu is looking like somewhat like y, and there is a plus here, but yeah, I mean plus is here also, that's fine, but then there is a negative fx here, but we have a positive. So it seems like while I will be changing infimum to supremum, I will do a negation here, and that will make it like minus. Okay, so essentially this is the plan. We want to kind of change infimum to supremum. To do that, we have to make a negative of the inside term. Okay, in that case minus nu transpose x will also appear, negative in front of nu transpose x, but that's fine, because then we will write it as f star of minus nu. Okay, so let us now try to change to the supremum. Okay, so this is equal to minus supremum of x, and as I said, if I have to change infimum to supremum, then I have to do minus of supremum of the negative argument of that, right? So that's what I'm trying to do. So this is supremum of the negative of this, negative of fx minus negative of nu transpose x. Okay, so now it's a matter of rearranging. This is minus y transpose x minus fx, and there is a negative also. So this is supremum of x, and let us rearrange this. So this is minus nu transpose x minus fx, right? So now we can write this as minus f star minus nu transpose. Okay, so this is minus f star minus nu. Okay, you don't have to put transpose there, just nu. So this is how g nu and conjugates are related via this optimization problem. I mean this is just like cooked up here to show you how they are related, but this still does not tell you how I will be solving a generic optimization problem. Not this is very specific. So if I am solving a very generic optimization problem, there how can I use f star? Okay, so that may not be still clear right now. Okay, so let us look into one of the examples where I can I can use f star. And the reason why we want to involve f star dual is because for many problems dual are known. Okay, they are tabulated. Okay, so if it's log, what is the dual? If it's x star, what is the dual? So transforming into dual conjugate, I mean, is a good thing. Okay, then you do not have to do all the calculations. So now let us look into an optimization problem which is more interesting than what we have written. So consider a following optimization problem: minimize f naught x. Okay, I may take few minutes more. Okay, if you are fine with that. I just want to, yeah, I know that's 7 minutes more, but I may take few minutes more. So subject to, I mean, if you want to leave, you can. The video will be there anyway. And Cx equals to d. So let us say we want to solve this more interesting optimization problem, and then I want to know how can I use, involve, engage f star, right? So let us see. So G lambda nu we can write, Lagrangian also we know, so we can straight away write G lambda nu, which is the infimum of the Lagrangian, which is f naught x plus lambda transpose, which goes with the inequality constraint. So this is ax minus b. Remember that you should always move the right hand side non-zero terms to the left, okay, before applying lambda, okay. So that's important. And then plus nu transpose cx minus d, okay. So we are supposed to infimize this. It is an infimum over x, so we can take out the terms which don't depend on x. So basically lambda transpose b and nu transpose d, they don't depend on x, so we will take them out. So here it's minus b transpose lambda minus d transpose nu plus, and the remaining term is infimum of x and f naught x plus a transpose nu plus c transpose a transpose lambda plus c transpose nu, and then whole transpose x. Okay, so we have simplified a bit. We have taken out the terms which don't depend on x and taken x common in the inside terms. So this is what we have. So now we want to see, right, how can we involve f star, right? So it seems like in place of y we have this, right? Again we can do the same trick, infimum change to supremum. So negative of supremum of the negative inside. So here I will have minus f naught x, and here I will have minus of this guy, right? So if we do that, then it's straightforward now. So minus b transpose lambda minus d transpose nu, and this is minus f naught star minus a transpose lambda minus c transpose nu. Okay, so all of you are fine with that? Okay, I did the rearrangement like I did before, and this is how I bring in the conjugates, right? So okay, I guess then we can stop for today. Okay, thank you.